Welcome to the last few days of the course. It's a little strange for me to be saying that because I do have to record this early in advance in order for it to be ready by the time Summer Quarter launches. So currently it's like the middle of May, but I can look into the future, and I know that you guys are in your last week of Summer Quarter as you watch this video. So congratulations, you've almost made it. We've only got 3 days of material to go and then final exams. Today we're going to take a closer look at vector-valued functions, and we're going to start talking about how to do calculus with functions that are vector-valued. Remember from when we studied parametrized lines that a vector-valued function was just a function whose output was a vector instead of a single real number. And those quantities could be used to represent things like the position of an object that's moving in 2 or 3-dimensional space. So we'll be looking at how to take the derivative and integral of a vector-valued function and what significance that might have in terms of a few real-world applications. Now let's quickly review some of the most essential ideas that we introduced when we studied vector-valued functions several sections ago. A vector-valued function was just a function whose output was a vector. So a list, an ordered list of 2 or 3 numbers, rather than just a single real number. And the canonical example is that the vector-valued function r of t points to the position of a given object at time t. Now, in Calculus 1, we studied the case of an object moving along a straight path, along a one-dimensional path such as a road, a wire, a tube, or something like that. If we knew that the object was moving along a straight path, then we only had to represent its position on that path using a singular number. For example, maybe an output of 0 corresponded to the center of the path, and maybe 2 corresponded to this location along the path, and maybe -2 was somewhere back along the path. For an object moving in one dimension, moving in a straight line, whose position could be measured with a single real number, the significance of the derivatives was given by the following. The derivative of position with respect to time gave the object's one-dimensional velocity. Velocity is speed together with some information about direction. In this case, in this one-dimensional real-valued case, the velocity was a positive number if the object was moving forward and the velocity was a negative number in the case that the object was moving backward along the path. If we had a scalar valued function representing position, then the derivative of position was velocity. What about if you took 2 derivatives? What was the derivative of the velocity? The derivative of velocity gave you the quantity that was called acceleration. And this told you how your velocity was changing over time, whether your object was speeding up or slowing down, or whether it suddenly changed direction and went from moving forward to moving backward. The acceleration is what gave you that information, and that was the first derivative of velocity, which is the second derivative of position. Finally, if you just wanted to know how fast the object was moving, and you didn't care about the direction in which it was moving, then all you had to do was take the velocity and take its absolute value. The absolute value of the velocity vector, the absolute value of the first derivative of position, was what we called speed. Speed is how fast the object moved the direction in which it was moving didn't matter. Direction matters for velocity. Direction doesn't matter for speed. Speed is how fast the object is moving independent of its direction. Now the beautiful thing is that if we have an object that's not necessarily moving along a straight line, but is moving maybe along a curving path in two-dimensional space, or is moving along a curving path in, say, three-dimensional space, then the velocity and the acceleration of the speed of the moving object can be measured in exactly the same way. The velocity can be found by taking the derivative of position. The acceleration can be found by taking the second derivative of position, and the speed can be found by taking the magnitude of velocity. So let's stop and let's talk about how to calculate the derivative of a vector-valued function as opposed to a scalar-valued one-dimensional position function. The beautiful thing about the calculus of vector-valued functions, about derivatives and integrals, is that just like vector arithmetic, vector calculus is component-wise, which means that we can take the derivative of the components one by one, and that will give us the derivative of the vector-valued function. If your vector-valued function is x of t, y of t, z of t, and you want to find the derivative of that vector-valued function, just take the derivative of x, separate from the derivative of y, and subsequently the derivative of z. Same thing with integrals. If you want to take an indefinite integral of a vector-valued function called r, written symbolically as integral symbol r of t and then dt to close, then all you have to do is take the indefinite integral of the x component, take the indefinite integral of the y component, and separately the indefinite integral of the z component. And likewise for definite integrals. If you're integrating from an initial t value to a final t value of a vector-valued function, then just do that integral of each component separately. So beautiful. I love vector calculus because it's exactly as simple as you always wish it would be. Just do it one component at a time. Just a quick note, I have given all of these formulas in terms of 3D vectors where we have a z component, but in case your object is just moving in two-dimensional space and your vector-valued function doesn't have a z, then the same general principles apply. For a 2D vector-valued function, you can still take the derivatives one at a time, integrals one component at a time. Let's just get some really quick practice with these formulas before we go into an actual application. For example, let's consider the 3D vector-valued function where r of t is given by cos in the x component, sine in the y component, and t in the z component. Somebody asks me for the derivative of this vector-valued function. So I can go in and I can calculate the answer one component at a time. And I can say, okay, well, what's the derivative of cosine? The derivative of cosine is minus sine. I can say, what's the derivative of sine? The derivative of sine is cosine. What's the derivative of t? The derivative of t is just 1. And that is how I get the derivative of the entire vector-valued function, of the entire, what's also called parameterized curve. R prime is the vector with those three derivatives in those three components. So someone now asks me for the indefinite integral of the vector-valued function. So I can calculate the indefinite integral of the components one by one. So I say, what's the indefinite integral of cosine? The indefinite integral of cosine is positive sine. But what is missing from my answer as of this moment? What do you always have to include when you calculate an indefinite integral that I have not included here? What's missing, of course, is the infamous plus c. So I'm going to include plus unknown arbitrary constant. Same thing for the y component. The integral of sine with respect to t is negative cos plus some other arbitrary constant. However, I can't use plus c in both of these positions because that assumes that the value of c is going to be the same number for both x and for y, and in no way is that guaranteed to be true. The number in the x's position is completely allowed to be different from this added constant in the y's position. So I'm just going to add a little bit of decoration to separate and distinguish these two numbers, give them different names to allow for the possibility that they're going to be different quantities. One I might call c sub x because it's for the x component. The other one I might nickname c sub y because it's the constant for the y component. Likewise, when I integrate t, I'll get t squared over 2 plus some constant for the z component. So my preference usually is to call that c sub z. Another way to reflect the fact that we'll have an unknown added constant in every component is to go ahead and say, okay, the indefinite integral is equal to sine t negative cos t, t squared over 2, plus a vector of constants. C with a vector arrow over top. To say that each one of these components, x, y, and z, has an unknown added constant, cx, cy, and cz respectively, is a vector of constants. So don't forget, an indefinite integral, an integral without limits, is a description of all possible antiderivatives of the vector-valued function. And so we have to be careful to include this plus c. Now when we have a definite integral, we don't have to worry about it so much, because a definite integral says, pick your favorite antiderivative, plug the limits into that, and then subtract those outputs. So in this case, I can take my favorite antiderivative from part B. For example, I could take sine minus cos t squared over 2 and plug the limits into that antiderivative. So plugging in the upper limits, I get sine pi over 2, then the lower limit sine 0, subtract those. Moving to the y component, I get negative cos 2 pi, take away negative cos 0. And then moving to the z component, I get t squared, so 2 pi squared over 2, take away 0 squared over 2, which is 0. This can be simplified to what looks like 0, since sine of 2 pi and sine of 0 are both nothing. Cos of 2 pi is 1, cos of 0 is also 1. So this is minus 1 plus 1, that's also nothing. And finally, if I take 2 pi quantity squared and simplify it and divide it by 2, the 2 squared over 2 becomes a regular 2, and then I have pi squared. So this vector is the definite integral from 0 to 2 pi of RT. Just calculate it component-wise. Finally, for part D, they say, can you find a particular antiderivative of R of t which satisfies this initial condition. When t is 0 and no time has passed, I want the antiderivative's output to be equal to the 0 vector. Now, when we calculated the indefinite integral in part B, we gave a general description of all possible antiderivatives of little r of t. Any antiderivative, in particular this antiderivative, capital R, must have the general format sine negative cos t squared over 2 plus some vector of constants. Now someone says, I want it so that when you plug in t equals 0, then the 0 vector is the result. But when I plug in t equals 0 to this result of the indefinite integral, sine of t when t is 0 is 0, cosine of 0 is 1, so I get minus 1 from the y component, and then t squared over 2 is 0, so everything is right except for that y component. And that's where this vector of constants becomes so essential. The vector of constants is necessary to get an antiderivative which satisfies this specific initial condition. The x component is fine, the z component is fine, but in order to get minus 1 up to 0, in order to get the y's to match, I need to make sure that my cy is positive 1, so that when it combines with negative 1, the result is zeroed out. As a result, the specific antiderivative that I need is r of t equals sine of t, and we didn't have to add any constant to that, negative cosine of t, but we needed to add 1 to that, and t squared over 2, we didn't have to add anything to that. This is the antiderivative which satisfies this specific initial condition. Basically, nothing has changed from Calculus 1 and 2. The only real difference is that instead of doing these calculations once for a single real value, we have to do these calculations 2 or 3 times, one for each of our components. Having practiced derivatives and integrals in general, I want to look more specifically at the case of motion, and at the case where r of t represents a position of an actual moving object. One of the quintessential examples of a moving object, in particular in 2 dimensions, is movement in a circle. For example, if you have an object which is attached to a string, which is being swung around and moves in a circle as a result of centripetal/centrifugal force. Now, we had an example in the parameterized lines video. In fact, we had several examples of objects moving in a circle. We studied an object moving in a circle of radius 2, which traversed the circle 1 time and made 1 revolution in 2 pi units of time. We had a third which traversed the same circle of radius 2, but it only took half as much time. It only took pi units of time to make a revolution around the circle. And we also saw in the second parameterization circular motion that instead of being counterclockwise was actually clockwise. Now let's generalize the work from that day. In that case, our sine and cosine were multiplied by 2, and that 2 became the radius of the circle around which we were moving. In general, if we want to move around a circle of radius r, then the only thing that we have to do is replace the multiplied 2 with a multiplied r. This particular parameterization will traverse the circle counterclockwise, and it will make one revolution in a time interval of 2 pi units. If we want to change the speed, if we want to make our object move at double speed or triple speed or quadruple speed, we just have to double up our t value or triple or quadruple our t value. So if I had cosine of a times t, cosine sine of a times t, where a is positive, this will just multiply the speed of the motion by a. Likewise, if you wanted to move in the clockwise orientation, if you wanted to move around the circle backward, then all you had to do was change the t to a minus t. This will traverse it clockwise with a circle of radius r multiplying by r. And likewise, this parameterization makes one revolution in 2 pi units of time. Again, if you wanted to change the speed to make the object move faster or slower, then you would do that by multiplying the t by an appropriate scalar. Let's do some physics exercises in the case of an object moving around a circle of radius, in this case 1. And since this t value is not being multiplied by any additional scalars, this is moving at the standard speed, making one revolution in 2 pi units of time. So let's recall that when we graph a vector-valued function, we are basically graphing the path along which the object moves if its position is measured by this function r of t. So when time was equal to 0, the vector pointed to this location on the right side of the unit circle where we had 1, 0. Then it moved counterclockwise up to the North Pole, then to the left, and then down. Whew, rough sketch, but it'll do. So let's also recall that a graph of a vector-valued function isn't complete unless we add some arrows to indicate the orientation of the graph, to indicate the direction in which the graph is traversed. I'm just going to write this word down, orientation, because this is a pretty commonly used word to refer to the direction along which the graph is traversed. They say, okay, so if RT represents the object's position, I'm interested in the object's velocity. I want to know at any given time, first of all, how fast the object is moving. Second of all, in what direction the object is moving. And for vector-valued functions, it's exactly the same as for real-valued functions. If you want velocity, then take the derivative of position. So I go in and I calculate r prime, component-wise. The derivative of cosine is minus sine. The derivative of sine is positive cosine. And if I want specifically the velocity at time t equals 0, then after I have found the general formula for velocity, then I plug in t equals 0. Remember, if you want to plug a number into the derivative, then you have to do that in a very specific order. Find the derivative first, then plug in the number. You can't plug the number in and then find the derivative, because the result will always be 0 if you do it in the opposite order. So I plug t equals 0 into this formula that I found component-wise for r prime. Sine of 0 is 0, cosine of 0 is positive 1. So the velocity vector at time t equals 0 is pointing straight up with a length of 1 unit. So this tells me that at time t equals 0, the object was moving upward, and the length of the velocity vector indicates the object's speed. So on the graph in A, I've gone ahead and followed this second half of directions. Draw the velocity vector on the graph with the initial point drawn at r of 0. Notice something interesting about this orange vector. The velocity vector at 0, drawn according to these directions, is tangent to the path of movement. Tangent in the same way that the tangent line from Calculus 1 was tangent. It points in the same direction as the path of movement. Follow-up question. Now that we have found the object's velocity, tell me the object's speed. Now the speed can be found from a velocity vector by finding its length. For a real valued function, these bars represented the absolute value. For a vector valued function, these bars represent the magnitude. But the fact that we have the same notation for both ideas, both the absolute value of a number and the magnitude of a vector, is really convenient, especially in this situation, because the absolute value of the first derivative of a real valued function has the same significance as the magnitude of the first derivative of a vector valued function. They are both indicating speed, so it's nice that we have the same notation. Now the length of 0, 1 can be calculated pretty easily. We have the square root of 0 squared plus 1 squared, which is just 1. So what's the object's speed at time t equals 0? The speed is just 1 unit. Maybe it's meters per second or something like that. Finally, acceleration. To find acceleration, we have to take the second derivative of position, which means we have to take the first derivative of the velocity vector. Now be careful, even though it's looking for the acceleration at time t equals 0, we have to take the second derivative of the velocity function before the 0 has been plugged in. As always, you can't plug in before taking the derivative, you have to plug in after taking a derivative. So if I take the derivative of the function negative sine t, then I get negative cos t. If I take the derivative of cos t in the y component, I get negative sine t. And now that that has been calculated, now I can calculate what I get when t is equal to 0 specifically. So r double prime, the acceleration, at time t equals 0, is negative cosine 0, which is -1, and sine of 0, which is 0. Now notice that if we actually graph the acceleration vector, then the acceleration vector, if I draw it with its initial point at the position of the object, then the acceleration vector is pointing straight in toward the origin. It's pointing in toward the center of the circle. That's not actually a coincidence. It turns out, and maybe I'm getting ahead of myself, when you study physics from a vector perspective, then the equation F equals mass times acceleration, F equals ma, this really famous equation from physics, also is true in vector land. The vector, the force vector, is a scalar multiple of acceleration, mass times acceleration. In other words, the force is parallel to acceleration. So when you have an object which is moving in a circular path, such as the one in this example, then there are a couple of quintessential examples of that happening. One of them being, for example, an object on a string that's being spun around. In that case, the force at work that's acting on the object is the force that is exerted by the string itself, pulling the object in toward the center of the circle. That force is pointing in the same direction, is parallel to the acceleration being undergone by the object, which is pointing in toward the circle's center.
So I've got a string tied to a tennis ball here, and I'm going to swing it in a circle. What I'm doing, I'm trying to swing it at about a constant speed, but I'm changing its direction all of the time because the direction of the ball, its velocity vector, is always tangent to its circular path. So that must require a net external force in order to do that. Where is that force being applied? Well, it's being applied by my hand. I'm pulling on the string. It's a force of tension. And which direction is that tension force acting? Well, I'm applying it with my hand through the string, and so it is acting toward my finger or toward the center of the circular path. So the tension force acts along a radius and toward the center of the path. And that is the force, the net external force, which we call centripetal force, which makes the ball move in a circular path.
As another example, one simplified model of an object's orbit around the planet is that an object will move around a planet in a circular orbit. In that case, the object at the center of the object's circular movement is the planet itself, and the gravitational force exerted by that planet on the object is pulling the object in toward the center of the planet. So the force and hence the acceleration both point in toward the center of circular movement. Now we can very quickly go through a similar example where this time we have a scalar on the t, on the input of cosine and sine. Now when we graph this movement, we're still going in a circle of radius 1 counterclockwise. And the initial position is still here at time t equals 0 on the right side of the unit circle. The only difference between the function here and the one in the previous example is that the object reaches every location earlier than it did before. For example, it reaches the left half of the unit circle when t is equal to just pi over 2, because that time will get doubled before it is fed into cosine and sine. Now let's see how that change in speed affects the derivatives of this vector valued function. If we calculate the velocity vector in this case, we have to be careful to remember to use chain rule, not just to calculate the derivative of the outer function cos, but to calculate the derivative of the inner function 2t. So this time our velocity vector has an extra factor of 2 that has appeared as a result of chain rule. And when I plug 0 in to this function, I get 0, 2, different from the 0, 1 that I achieved last time. This velocity vector is pointing in exactly the same direction. The movement of the object has not changed direction, but the velocity vector is twice as long to reflect the fact that the object is moving twice as fast. Now we can confirm this by going ahead and calculating the object's speed, the absolute value, the magnitude of the velocity vector that existed at t equals 0, which was just the square root of 0 squared plus 2 squared, the square root of 4, which is 2. So the object speed at time t equals 0 is equal to 2 units of speed, perhaps 2 meters per second. Likewise, we can go ahead and we can graph the acceleration vector. Let's calculate the second derivative by taking the first derivative of r prime, and we get negative 2, so constant multiple, times the derivative of sine 2t. So another 2 actually is going to come out, and we get negative 4 cosine 2t. Another 2 is going to come out, and we get negative 4 sine 2t. This formula gives the value of the acceleration at any given time. If I then, after having found the derivative, plug in the given time t equals 0, then I get negative 4, 0, which is actually 4 times as long as it was before. So to properly graph this acceleration vector, it would have to be 4 units long, so pointing all the way here to the left side. Folks, I'm so sad. I just recorded like half an hour of footage, and it turns out that my recording software was paused the entire time. Oh well. But I think that this is a good opportunity to maybe reevaluate the way that I had things ordered. I think I had too much material scheduled for today anyway. So I have decided actually that I'm going to make this the last piece of material for today. And I've decided actually that in terms of learning objectives, I'm going to move this last one so that it's not today, but so that it's actually tomorrow. So the last thing that I'm deciding to cover for today is motion along the graph of a function. We focused quite intensely on circular motion because it's such a typical example that comes up in particular in calculus-based physics classes. However, in general, if you want to represent an object moving along the graph of a algebra type function, then there's a really easy way to do that as well. For example, suppose that your object was moving along a roller coaster track in the shape of this parabola. How would you parameterize such a thing? The goal for your parameterization, x of t, y of t, is for the x and y of your parameterization to actually make this equation true. If the x and y make the equation true, then the x and y will always point to a location on the graph. So we need the y of the parameterization to be equal to the function evaluated at the x of the parameterization. And then there's one very simple and trivial way to get this done. Basically just a change of variable. just replace the x with the parameter t, and then plug the t into the function to get the y. So the graph of a function y equals f of x can be parameterized simply by letting r of t be the vector valued function with t in the x component and the output of the function at t in the y component. This will, as t increases, steadily move from left to right along the curve. T increases, so the x component increases as well, and then the y component adjusts so that the height of the vector always is such that you're pointing to a location on the graph. For example, in the case where we had y equals x cubed, a parameterization for that would be given by x gets replaced by the parameter t, and let y equals t cubed instead of x cubed. Easy. When you graph this, you'll get exactly the same shape. It's just that this time we understand that the object is moving along the graph from left to right. If this is the object's position, find the object's velocity. Find r prime, find the velocity vector specifically at the time t equals 1. So the first thing that we need to do, always, the first thing is find the derivative. Do that before plugging in the given time. The derivative of t is 1, and the derivative of t cubed is 3t squared. Then, let's plug in 1 after having found the derivative, and we get 1, 3. Now they want us to graph this vector on the graph of the function where the initial point of the vector corresponds to the object's position at that time, which is given by the output of the original function. So let's grab that information real quick. The output of the original function at time 1 is 1 and 1 cubed. So that's that point right here, 1, 1, right here on the graph. If I plot the vector 1, 3, the velocity vector, starting from that position, we'll get the same kind of graphical relationship that we saw in the circular motion section. The graph and the velocity vector are tangent. And that's something that we will be exploring a lot more starting tomorrow. What if we wanted to take this vector in pink here and extend it into a full line? How would I parameterize the line where the direction vector was r prime and the point on the line was the original function r? There was a really easy way to get the parameterization of a line. I'm going to call it L for line, since r is taken. Just take the direction vector, in our case r prime of 1, scale it by the parameter t, and add the initial location. In our specific case, our direction vector was given by the vector 1, 3 from part B. And our vector r of 1 was 1, 1. And if we graph this line together with the function y equals x cubed, we can see that this line is actually tangent to the curve at that point. So LT is tangent to r of t at t equals 1. So that concludes what I'm going to talk about today. Tomorrow we're going to talk more about the idea of a tangent vector and a tangent line. We just saw an example of that. The vector r prime of 1 was an example of a tangent vector to the curve, since it was graphically, literally tangent to the curve. And the green line, which was the extension of that vector, is a tangent line to the curve. But that's tomorrow. Today we focused on vector-valued functions, reminding ourselves how to graph them, looking at how to calculate derivatives and integrals of vector-valued functions, looking in particular at applications to movement. The first derivative of position was velocity. The absolute value of velocity is speed. The derivative of velocity is acceleration. We did that in the case of circular motion, and we did that in the case of an object moving along the graph of an algebra function y equals f of x.